So we were analyzing self-adjoint operator. Let X be a self-adjoint operator. And sigma X spectrum. Then we have functional calculus, a map F in C of X, C of sigma of X to C star. I mean, we can associate for this, we can associate a map from here to, I mean, this is the representation, you can call it pi if you want. We can associate a map f of X is an operator in the C star algebra generated by X and Y. Okay, so this one I am including for the purpose of making it unitary. So then we can extend this map to further, we have, this is what is called continuous functional calculus. Included. Similarly, if you then there exists a measure mu on sigma of X, B of sigma of X, Borel sigma algebra of sigma of X, such that we can associate something called measurable functional calculus. We have from L infinity sigma of X mu to C star algebra, sorry, this is not C star algebra, to B of H, okay, B of H. I mean, this will be what is called a Finite algebra generated by that. So since we haven't introduced that, I am not saying. So this again, if you have a F here, then you will get a F of X in B of X. So this we can do for any measurable function on the sigma of X. So in particular, we can do it for the characteristic function of any set or any indicator function. So for any subset of the spectrum, we can associate something. And since an indicator function is a idempotent, it's a projection, its square is itself and it's its own self-adjoint, we will get a projection here. The corresponding f of X will be a projection here. So if we have E is a subset of sigma of X, then we can associate 1E of X is a projection. It's a projection. And all as all this L infinity is a commutative Banach algebra, commutative C star algebra, all these things commute. I mean, this 1EX will commute with EX and all the operators corresponding to this f of X. All these f of X, these operators, functional calculus operators, they commute with each other. Okay. So, but then we don't need to restrict this projection to just sigma of X. We can take any subset of complex number. Since it is self-adjoint, sigma X will be contained in the X is self-adjoint. So sigma X is contained in real line. So if you have any subset of real line, then you can take the intersection with the spectrum and call that, and then you can associate that projection. Okay, so if you have any subset, E in particular any interval, E contained in R, then you can define this 1E of X to be 1E intersection sigma of X. Okay. And this range of this projection, this is what M, E, X is range of 1, sorry, MXE. So this is the confusion in the book. So I'm just following the notation in the book. MX. So here this is a function of the set. Range of 1x. Then we prove some properties of this projections. In particular, we proved, I don't want to recall everything, just some properties. We proved that if you have T naught in the spectrum, sigma of X, then you can associate this T naught minus epsilon, T naught plus epsilon. Okay. This is not equal to, this is not trivial. This projection, this subspace is non-trivial for all epsilon greater than 0. We proved this. Okay. This subspace is not equal to 0. It's non-trivial. Okay. We proved this, and we also proved that you can take the intersection and you can talk about mx of singleton t0, and that is equal to kernel of x minus t0. That also we proved. Okay, so then we can transform many of the properties of the function to the operators, corresponding operators. Anyway, so after this we proved something called a Helmholtz criterion. That is, so we proved, I'm just recalling what we proved. We also proved if we have a x in this some -1 1, this is equivalent to saying this x power n x is bounded. This p sequence is bounded in n. Okay. So this also we proved. So using this, we got a corollary saying that if x some y self-adjoint and commutes with xy equal to yx, then y commutes with all spectral projections. I mean, these are the spectral projections, commutes with 1ex. I mean, 1ex for all x in, sorry, for all e in e subset of r. Okay. So we proved this also. So we want to use these things. So next so we have proved it's not spectral theorem, but something like spectral theorem. From that we will get the spectral theorem. We proved some sort of spectral mapping theorem. We associated a kind of functional calculus for a spectral self-adjoint operator. So we want to do the same thing for any normal operator. So before doing for a normal operator contains two commuting self-adjoint operators. We have a normal operator t, then t is equal to x plus iy. It is given by x. It is x plus iy. So where this is t is normal if and only if x and y commutes. Okay, that we know. So instead of only restricting to this kind of commuting, I mean this kind of x plus iy, we can talk about general polynomials in commuting self-adjoint operators. So we want to prove a functional calculus for a commuting family of self-adjoint operators. So then we can talk about, we want to define a joint spectrum for a family of commuting. We want to talk about finite family of commuting self-adjoint operators. So this is what we want to discuss. We want to take a collection of self-adjoint operators, finite collection of self-adjoint operators, and we want to define a joint spectrum, and we want to associate for any function in the joint spectrum, either continuous or measurable, we want to associate an operator here. We want to associate a corresponding operator. So that it's an isomorphism between the function algebra, which is C-star algebra, with the C-star algebra generated here. So this homomorphism. We want to define a star, indeed an isomorphism, star isometric homomorphism. That's what we want to talk. So throughout this class, fix commuting. We fix arbitrary, but fix a commuting of self-adjoint operators. Self-adjoint operator x1 up to xn in B of h. So then we define the following definition. Define the spectrum. This is what is called x1 up to xn. This is what is called joint spectrum. We know when we have only one self-adjoint operator or even a normal operator, then the spectrum is nothing but the collection of all approximate eigenvalues. In finite dimension, spectrum means all eigenvalues. But in infinite dimension, for a normal operator, not for a general operator, any lambda is in the spectrum if and only if it's an approximate eigenvalue. Here we want to use that idea. We want to extend. We don't want to define this joint spectrum through invertibility. We want to use, through the concept of invertibility, we want to use the approximate eigenvalue concept, and then we want to define this. So this is the definition of the sigma x1 up to xn. This is all those lambda 1 up to lambda n. Okay. So this will be usually in Cn, but here it's self-adjoint, so it will be in Rn, such that what happens. So there exists a Xn, a family Xn contained in the Hilbert space H, such that norm Xn satisfying norm Xn, I mean contained in the unit ball of H, norm Xn equal to 1, such that this thing happens. Xi minus lambda I Xn goes to 0. Okay, as n goes to 0. The same, I mean, it is just the joint approximate eigenvalue, I mean, eigenvalue for all of them. I mean, you have a joint approximate eigenvector. I mean, the eigenvector is not a single vector, it's sequence. Okay? So Xn for all this lambda 1 up to lambda n. Okay? I mean, the eigenvalues are different, lambda 1 up to lambda n. You have a lambda 1 up to lambda n. This Xn is a joint approximate eigen, I mean, it's not eigenvector, it's not a single vector. It's a giant, you can call it eigenvector if you want. Approximate eigenvector for all these things, for all this lambda 1 up to lambda n. Okay, so the definition is clear. So, okay, so we want to prove similar properties as, so this is the spectrum we want to consider for a family of operators. Okay. So, family of self-adjoint operators. This is for self-adjoint operator we want to prove this. Later we will prove the similar thing for normal operator also. That's after proving spectral theorem for normal operators. So, now the proposition. So, first one is this is compact. It's a compact subset of Rn. Compact subset of Rn. It's a subset of Rn. So, second thing. So, it's compact. Then, so so this is a subset of Rn. Then you have the coordinate projection in Rn. Okay, let P or I is from Rn to R is a coordinate projection. Projection on ith coordinate. Okay. Then this P or I of this sigma, maybe sigma 1 up to sigma x1, let's write x1 up to xn, is nothing but sigma of xi. Okay. In particular, this is not empty. I mean, you have the coordinate projection. Each coordinate projection is not empty, so this is not empty. Okay, the proposition is clear. First, we want to prove it's compact. Then we want to prove that it's when you apply the coordinate projection, you get the sigma of xi. For each coordinate projection, you get sigma. So we want to prove this subset is compact. To prove compact, we have to prove it's closed and bounded. First, notice that it's bounded follows because, I mean, we have a sequence of approximate eigenvectors, which is a joint eigenvectors, joint approximate eigenvectors for all of them. In particular, it's an approximate eigenvector for each of them. So this will imply that so if we have a lambda 1 up to lambda n in this set, then each lambda I is in sigma of that, sigma of xi. Okay, it's contained in this. Right? I mean, if you have lambda 1 up to lambda n in this, that means there exists an approximate eigenvector for this. In particular, that's an eigenvector for each lambda I. So that means it's in the spectrum. So that is in the spectrum. Okay? So this is in the direct product of sigma of xi. Okay? So this implies, in particular, this implies sigma of xn is a bounded set. Is bounded. It's a bounded set subset of R. Okay, now we want to prove it's closed. Okay, so to prove this is closed, I mean, when it is clear, I just write sigma, not sigma x1 up to xn is closed. So we are proving one is closed. So let some lambda 1n, lambda 2n, to lambda. So I have taken x1 up to xn, is it? Maybe I can change it to k as, okay, let me take m. Maybe take k here. And necessarily, I should have taken it k, but since I don't want to change it with that. So I take lambda 1k, lambda 2k up to lambda nk. It's a sequence in k. Usually sequence is in n, but here I'm taking it in k. So this is a sequence in k, k in n, some sequence in okay, such that it has a limit, it converges to something, then we want to prove the limit is also there. We want to prove it's closed, such that this lambda, so in particular lambda I k converges to lambda I. I mean, that's what it means. It's a finite tuple, okay, for all I. So then we want to prove that lambda 1 up to lambda n. We have got a lambda I as a limit of this lambda I k. Then we want to prove this lambda 1 up to lambda n is there. Lambda 1 up to lambda n is in that sigma. Okay. Okay. Now we know that lambda I k converges to this. So what do we have to prove? We have to find a, so we want to prove something is in sigma. By definition, something is in sigma if we can find an approximate eigenvector. It's a sequence of vectors, unit vectors, which forms an approximate eigenvector for that. Joint approximate eigenvector for that. Okay. So to get that, what does it mean? So joint approximate eigenvector means you have something like this: xi minus lambda I. We want the sequence xn, okay, with norm xn equal to 1. It's a subset. It's a subset of the unit ball of the Hilbert space, such that this xn goes to 0. Okay, that is we want given epsilon greater than 0. This is for all I. Given epsilon greater than 0, we want an x. I mean, this xn, instead of xn, you can take epsilon equal to 1 by n and prove it. It's enough to prove this. Okay, we want to find an x in h with norm x equal to 1, okay, such that xi minus lambda I x is less than epsilon. That's what we want. Given any epsilon, okay, given any epsilon, we want to find a x satisfying this for all I. Okay? That's what we want. So, but we can find this x, I mean, which will depend on n. We can find it for that sequence. We have a sequence which is converging to this lambda to lambda n. There we can do this. And further, we have a, choose n naught such that lambda I k, no, sorry, this is k naught, since I have used the sequence. This is k naught. Okay, lambda I k is just naught. K minus lambda I is less than, say, maybe epsilon by 2. Okay? Epsilon by 2. Okay? You choose k naught such that this happens for all I. Okay? Now for this k naught, there exists an approximate eigenvector for this. Okay? For this, this lambda I k, lambda 1k, lambda 2k, lambda 3k, lambda nk, for this k naught. So now choose. There is an approximate eigenvector, which is a sequence, but that just means given an epsilon, you can find a x which forms an approximate eigenvector. Epsilon, if you want epsilon approximate eigenvector. So now choose a x in h with norm x equals to 1, such that xi minus this lambda I k naught, okay, this norm of this x is less than epsilon. Okay. So after fixing, getting a lambda I k naught, I choose an x for this. Now it's clear. Now xi minus that lambda I, which is this triangle inequality, which is to take that epsilon minus that epsilon. Since norm x equal to 1, this is less than epsilon. Okay? This is a triangle. So this implies lambda 1 up to lambda n is 0. It's fine. It's just the usual epsilon by 2 trick. Okay. But the next one is bit non-trivial. This is okay.
Yes, sir.
This is easy. So next we want to prove. So we have proved that it's a compact set. Okay. We have proved that when we noticed that this joint spectrum is contained in the direct product of it need not be equal to that. I mean, there are examples where you can take the same x, for example. I mean, it will not be equal. Okay, it is just contained in sigma of x, right? But if you project the coordinate projection, you will get that. So that is, I mean, that does not mean that it has to be a direct product. Okay, you can, I mean, the coordinate projection may be equal to some set. That doesn't mean the big set is just the direct product. That will not be the case. Okay, so we want to prove that the projection onto the ith coordinate is just the sigma of the corresponding and the spectrum of the corresponding operator. So now to prove, we take the projection of ith projection of the sigma equal to sigma of xi. This is what we want to prove. So we prove this by induction. Okay, we prove by induction. So for I mean induction in n. Okay, in the in the number of commuting operator we choose. So when there is only one operator, this is just clear. I mean, we know that, I mean, this is defined through approximate eigenvalue. And we know that approximate eigenvalues coincide with the spectrum for normal operator. Here it's self-adjoint, of course. So clearly true for, so we know that this is true for n equal to 1. It just says the approximate eigenvalues of normal operator is same as the spectrum. That's what it says. So it is true for n equal to 1. Okay, now suppose true for n, we want to prove it for n plus 1. Okay. So to prove for n plus 1, we need to prove the following. Okay. To prove this fact for the n plus 1, see, one thing you should know that, I mean, this is this x1 up to xn, there is nothing about the ordering. Okay. I mean, these are all commuting operators. So you can take whichever the order you want. I mean, there is nothing about the ordering. So you can choose. So you want to prove that the projection of the nth one is. So it's enough to prove this. To prove for n plus 1, enough to prove the following. Enough to prove for lambda k plus 1 in sigma of x k plus 1. I mean, I used n. No? So this k and n, maybe I should change in the next proposition to k rather than n. Okay. Lambda n plus 1 in xn plus 1. Okay. Enough to prove for there exists a lambda 1 up to lambda n in the sigma x1 up to xn. I mean, we have operators x1 up to xn plus 1. Enough to prove for n plus 1 means enough to prove for this. Let's assume this x1 up to xn plus 1. We know this is true if you take n commuting operators. I mean, we are assuming it's true for n commuting operators. We want to prove it for n plus 1 commuting operators. Okay, and it's true for n equal to 1. So so enough to prove if we have a lambda n plus 1 and sigma of any lambda, any arbitrary lambda n plus 1 in sigma of n plus 1, we can find a lambda 1 up to lambda n in this x1 up to sigma of capital sigma of x1 up to xn, such that this lambda 1 up to lambda n plus 1 is in sigma of x1 up to xn plus 1. So it's enough to prove this. So by our induction hypothesis, this is the sigma x1 up to xn satisfies that property. In particular, that is non-empty. Okay? So it's enough to get this. Okay. Okay. I hope you can hear me from this distance. Okay. Because it was dark when I keep it there. So, okay. So given a lambda n plus 1, we want to get this. How do we do that? We do the following. So let us take the projection. Okay, let Pn equal to this projection 1. So we have lambda m, no? So we take this open interval, lambda n plus 1. So this has to be k. Sorry. I should have taken that as n, this as k, but since I have changed it, I mean, pk equal to lambda 1 by k, lambda n plus 1 plus 1 by k. You take this open interval of length of, I mean, open neighborhood of length 1 by k of this lambda n plus 1. This interval lambda n plus 1 minus 1 by k, lambda n plus 1 plus 1 by k. You take this open interval and take the projection corresponding to the of this xn plus 1. Xn plus 1 is a self-adjoint operator, so you can define this spectral projection corresponding to that using functional calculus. Okay. So now all this, we have proved that, I mean, the earlier using the Helmholtz criterion, whatever that criterion, if something is in the spectral projection that is corresponding to that, some sequence is bounded, some norm of some sequence is bounded. X power n something is bounded. Using that, we proved that if some y commutes with x, then y commutes with all spectral projections. We proved that. So in particular, all this x1 up to xn commutes with this pk. Okay? And something commutes with the projection means it's leave the space invariant. Okay? This I think we have did we notice somewhere? I mean, it's clear from the linear algebra course. I mean, if you can just write it, if you see, if you, in case you don't, some of you have noticed it. If you take any projection, you can write it like this, right? And any operator with respect to some subspace. If you have some Hilbert space, I mean, I will erase this. If you have some subspace of a Hilbert space, and P is the projection corresponding to this H0, then using this H can be written as H0 direct sum H0 per. Okay, so this is this. So then you can write it as a 2 cross 2 matrix containing operators. This is the identity operator on H0. The projection can be written like this: 1 0 0 0. Okay, and any operator can be written like this. Okay, and then composition of operator is just the matrix product. Okay, then you can, so x can be written like this. So something x commutes with p means you can write the equation, write the px equal to xp and compute the matrix entries, equate the matrix entries. Okay, you will get that x2 equals 0, x3 equals 0. So it will look like x equal to, it will look like 0 0 x3. It will just look like this. Okay? You can, I mean, it's just an easy exercise. Okay, so if an operator commutes with a projection that is equivalent to saying, it leaves the subspace corresponding to the projection in there. It is a direct proof. You can verify this. It's a simple exercise. So if you have any if you have x1 up to xn, they commute with the operator x. So it will commute with all the spectral projections. Okay. So something commutes means then you can restrict that operator. I mean, an operator will look like this: something here, 0 0. Then you can take this as an operator and consider that as the restriction. Okay. So you can talk about pk xi. Okay. So you can okay. we have all this pk xk, pk x1, pk xk. So if you, I mean, you can multiply with the projection since they commute. Two self-adjoint operator commutes, then the product is also self-adjoint. Okay. So this is actually contained in this is n. Right? Okay. This is actually contained in this. That is clear, no? This is just all. I mean, this later part. This left-hand side. This left-hand side is just all those approximate eigenvalues. So you get which has approximate eigenvectors inside the space, inside the subspace pk. Here it's in a bigger space, so this will be contained in this. Okay. In particular, if see, I will write the statement. If it is not clear, you tell me. I will just write it. Since pk decreases in k, that is because the sequence decreases. The pk corresponding to this indicator function, and those functions are decreasing. Okay, so the sets are decreasing, so the space will also decrease, right? Okay. It comes from the property of the function. That if you take this function, one e is contained in f. Okay, then one e is less than or equal to 1f. So this will imply the corresponding projection is also less than or that. The projection is less than that means that subspace is contained in the other subspace. Okay. It's these things you should write down and check it. Something is less than means as the difference is positive. So something this x is greater than 0. That just means that one is contained in the other. You can prove that for projections. Okay. We can prove that if x is here, then x is in the bigger space. Is this okay? Is this okay? Whatever I'm saying. Anyway, you can verify these things. It's an easy exercise. Okay. So since this pk decreases in k, this sigma of pk x1, which are subsets xn, decreases in k, right? If you have a smaller k, that means you have a vector in the pk. You have a vector in the subspace pk. Okay? Or you can consider this as restriction. I don't want to write it as restriction. So this just means, if you have these operators are 0 outside the subspace pk. They just act on this pk and it is 0 outside the subspace. So if you want to get a non-zero vector to form an approximate eigen, that has to come from that. Okay, that has to come from that subspace. So, and satisfy some property. So if that satisfies that property, it will satisfy for a bigger space. Okay. So sigma of this will be contained in a bigger k. If k is less than k prime, then the sigma of whatever this set I have written in k is contained in the sigma of the whatever the set in k prime. Okay. Is decreasing in k. It's fine. So this is a decreasing compact set and they are non-empty. So if you take intersection of finitely many of them, that is non-empty. So the whole intersection is non-empty. This is a compact, this is a decreasing. So this is a decreasing, this sigma pk x1 up to pk xn. Okay, these are all contained in Rn. Is a decreasing family of compact set. Okay, and it satisfies. It's clear that it satisfies finite intersection property. Whatever it's called. I just want to mean that if you take any finite collection of this, finite subset of this, then their intersection, I mean, it's a decreasing set. I mean, the smallest of them will be the intersection. So they are all non-empty subsets. So the intersection is non-empty for any finite sub-collection of this. So since it is compact, since they form a compact set, so this is a decreasing collection. Okay? They are all contained in the first one or something. This is a compact collection. So since they are compact, this implies this intersection is also non-empty. The intersection of K in N
intersection theorem, right?
Yes, finite intersection theorem. Right?
Cantor intersection theorem.
Is that okay? This is okay. I'm not saying diameter goes to 0, no, something like this. Cantor intersection theorem says diameter needs to go to 0. This is just finite intersection property of the compact set. They are all compact subsets of big compact set. Any compact satisfies something called finite intersection property, which is just the complement of the every open cover has a finite subcover. Every open cover has a finite subcover. If you take the complement of this property, if you have a collection of closed set which satisfies the finite intersection property. See, if something covers the whole thing, means you take the complement, that will be, see, every open cover has a finite subcover. So everything which is not everything which does not have a finite subcover cannot be a cover. I mean, does not have a, yeah. You just take the complement of that statement, you will get that if you take any if you take a collection of closed set which has the finite, if you have a collection of subsets of a family of subsets of this compact set, if you take the intersection of finitely many of them, that is non-empty. That means you take the complement, that cannot be the whole, that is non-empty, means that the complement cannot cover the whole thing. Okay, so the whole cover cannot cover the whole thing. That's what it means. If you have a collection, open set collection, whose any finite subcover cannot cover the whole thing, that means the whole open cover cannot cover the whole thing. It's not open cover, the collection of open set. That's what it means. That's what it means by a compact set. A compact set means every open cover has a finite subcover. So if we have a collection of open set which does not have a finite subcover, then the whole thing is not a cover. Okay, whole thing cannot cover the whole thing. I mean, the whole family cannot cover the whole set. Okay, so the complement of this statement is if you take finite intersection property. Okay, that's what I'm using, not the Cantor intersection. That needs the diameter has to go to 0. Okay, so this is not equal to empty. Okay, so choose lambda 1 up to lambda n in this intersection. Okay, in this intersection. Okay. So now this lambda 1 up to lambda n is in this intersection. That means it is an approximate eigenvalue for all this set. Okay. So now for k, choose xk in H with norm xk equal to 1, such that what happens. So for any k, this lambda 1 up to lambda k is in the sum of this set. I mean, for any k, this lambda 1 up to this tuple lambda 1 up to lambda n is in that set, sigma of that corresponding set for k. Okay. Norm of x, you can write it whichever the way, I mean, you can write it xpk or pkx, doesn't matter, they can be good. xpk, xipk minus lambda I x is less than 1 by k, right? So this has to be xk. Okay, you can choose such an xk. Okay, because there is approximate eigenvector for that. We want to find a one. I mean, we are going through some kind of diagonal argument. For each xk, we want to use the 1 by k for 1 by k approximate eigen. I mean, for any epsilon, we can find an approximate eigenvector. So for the 1 by k, I take the For the kth thing, I take the 1 by kth approximate eigenvector for this lambda 1 up to lambda k. Okay? This is for all I less than or equal to greater than 1. You have chosen something like this. Okay. Okay. So this is satisfied for all this xi. And in particular, it will satisfy for x also. This is equal to, this xk is in range of pk. So in particular, this is also equal to xi minus lambda I xk. Okay, that is equal to that. So this is for I between 1 to n. So what happens for I equal to n plus 1? But for I equal to n plus 1, this is automatically satisfied. Now xk is in pk. Now xk is in range of pk, but which is nothing but range of this set. Lambda n plus 1, no? N plus 1 minus 1 by k, lambda n plus 1 plus 1 by k. That is what we started with, okay, of this x n plus 1. Okay. So this implies xn plus 1 minus that lambda n plus 1 of that xk is actually less than 1 by k. If you want, you can use this property. This function, if you have t, you take this function. This is just function lambda n plus 1 minus 1 by k, lambda n plus 1 plus 1 by k. This function 10t times t minus lambda n plus 1. This function satisfies this is less than 1 by k. So this will imply you take this function, whatever in this modulus, that function has L infinity norm less than or equal to 1 by k. So this map functional calculus in isometry, so that will imply this norm of this is also less than or equal to 1 by k. But this xk is a unit vector, because of that this will fall. Okay, I'm not writing, I said all these things, but it's clear from the functional calculus. I mean, these things, I have given the reason, but I think you should write and convince yourself. Okay, then only you will understand the functional calculus. Okay, so convince yourself. I have given the reason orally, all the arguments orally. If you need something, you can get convinced yourself. Okay, so this is true. So this just means lambda 1 to lambda n plus 1 is in, we just got is in sigma is in sigma x1 to xn. Okay. What we have proved is, given any lambda n plus 1 in the spectrum of xn plus 1, we found a family, we found a tuple lambda 1 up to lambda n, such that lambda 1 up to lambda n is the joint spectrum of x1 up to xn. And this whole thing is in the spectrum x1 up to this lambda 1 up to lambda n is in the spectrum of this. Okay. So this implies if we take the projection in the n plus 1 thing, you get sigma. This implies projection of n plus 1 of this sigma x1 up to xn plus 1 is just sigma of xn. Okay. Just sigma of xn. This xn plus 1 is nothing special. We can take it from the middle or in the, that's not matter. We are just adding one more thing. That's what this says. Okay. The proposition is proved. So you tell me whether it is okay with everyone. Otherwise, I will go through the argument. The argument is we want to find an approximate eigenvector. We took a projection, spectral projection of xn plus 1. Then we found eigenvectors in that spectral projection decreasing to 0, and then use some property and use the property of the set to get an approximate eigenvalue for that. We did something manipulation. Okay. Is it fine? Anyway, go through it. If you have doubt, you ask me later. Okay. Okay. So this is actually supposed to be a lemma, whatever I stated. This is the main theorem we want to prove. So the theorem is the following. This is the spectral mapping theorem. I mean, polynomial spectral mapping theorem. You can, the spectral mapping theorem is true for any continuous function or measurable function also. Okay. But to prove that, we first use the polynomial functional calculus. Polynomial spectral theorem. I mean, to get functional calculus, we use polynomial functional calculus and extend it by continuity. So the same thing. Okay. So for that, we need this spectral mapping theorem for polynomial functional calculus. So if P is a polynomial, n variable polynomial. I mean, it's a polynomial in Rn, but we want to consider this a function in this sigma of x1. So now I change it to xk, okay? So that it will not be, but we are not going to take sequence anymore. So maybe we can keep it as xn. Are we going to take? No. Okay, I keep it as same. So P is a polynomial on X joint spectrum of x1 up to xn. Okay, then we can consider, I mean, if you have x1 up to xn, then you have a n variable polynomial and you have n operators which are commuting. Even if it need not be commuting, you can insert it in the polynomial, and using the algebraic relation, you can get an operator. Because this cells are finitely many things, finite sum and finite product. It makes sense. It's just an algebraic way of, it's an algebraic product, and you algebraically you get an operator. Okay, so you can talk about P of x1 to xn. If you have any n variable polynomial, you can do this. And this is a complex polynomial. Okay, it's a complex polynomial. Okay, so you can do this x1 up to xn, and they are self-adjoint operators. So self-adjoint, so the commutative, I mean, even if it is not self-adjoint, you have to take non-commutative polynomial. I mean, the polynomial, how you write the product matters. X power n, y power m, all this is matter. But here it does not matter. Here it's just the x1 up to xn commute. So the polynomial you can just substitute, and it does not matter how you write it. Okay. Otherwise, you have to write it x power n, y power n, then you may get an x power k or something. I mean, you have to worry about the commutativity. Here you don't have to worry about it. So x1 up to, see, we are for this class we are fixing x1 up to xn. They are commuting family of self-adjoint. Okay, so P of x1 up to xn makes sense, which is an operator. Okay, this is a single. I mean, this is a polynomial, so you get a single operator. So this is an operator in P of h. It's not a tuple of operator. It's just a single operator, P of h. Okay, so then. So you can talk, you can ask what is the spectrum of this. So since x1 up to xn are self-adjoint, you have a complex polynomial, it will be a normal operator. So then, okay, let me be right. Then P of x1 up to xn is normal, is a normal operator, and this is the theorem. P of sigma of P of x1 up to xn, as you expect, we have already seen P of sigma of x1 to xn. This is a polynomial functional calculus. Okay, polynomial spectral theorem. It's fine. Okay. So maybe I should give an exercise here. Okay. Okay, we will prove the one is, this is left hand side is included in the right hand side is included in the left hand side. I think one way should be clear. So first, if if lambda 1 up to lambda n is in sigma of x1 to xi, okay, that is, what does it mean? That is, there exists a xk, When I wrote the definition, did I write xk or xn? No, just to make sure. See, here I have written xn. Should be xk, no? The definition of joint spectrum, it should be xk as k goes to. So there exists a sequence xk of unit vectors such that norm of xi minus lambda I xk goes to 0, k goes to infinity for all I. Right? So something is in the giant spectrum. Now we want to prove that this means, so we want to prove one way. Okay, so first to prove this inclusion. Which inclusion? Sorry, the other inclusion. To prove this inclusion. Okay, first to prove this inclusion. So I take lambda 1 up to lambda n in this sigma x1 up to xn. Then I take polynomial of that lambda 1 up to lambda n. That should be in this spectrum. That's what I want. Okay, I'm proving this way. Okay, so that's what I have to prove now. I want to prove the right hand side is contained in the left hand side. So I take a lambda 1 up to lambda n in the joint spectrum of x1 up to xn. Okay. Then I take p of lambda 1 up to lambda n. Okay. I insert it in the polynomial and get p of lambda 1 up to lambda n. That should be contained in, that's an element in this spectrum of the polynomial of x1 up to xn. Okay. So lambda 1 up to lambda n is in the joint spectrum, means there is approximate sequence of approximate eigenvectors like this. That's what it means. I just have to prove that if you take the polynomial in p of x1 up to xn, then the corresponding p of lambda 1 up to lambda n, the polynomial in lambda 1 up to lambda n, when you insert the lambda 1 up to lambda n in the polynomial, when you insert the x1 up to xn in the polynomial, then the corresponding should be in the spectrum of that. That just means that has to form an approximate eigenvalue. So we want then, I mean, this is true, p of x1 to xn, then claim. See, this I want to give it as an exercise, but it's easy. I'll tell you how to do that. This is a number, p of lambda 1 up to lambda 1 is a number. Okay, this is an operator, single operator of this xk also goes to 0. Okay. So why is this true? So a polynomial is a sum of some degree x power n something, some x power n, y power n kind of thing. And the sum, so if you write like this, then the corresponding coefficient you can just match, and by triangle inequality, you just have to prove that. So this is, I leave it as an exercise. Okay. You have to only worry about the powers of this x1 power n, n1, x2 power n2, xn power n, so m1 maybe, m2, mn. Okay. Now you have to worry. So you have to worry about these terms only. I mean, the polynomial will look like this. There will be a constant here times something like this, and some. I mean, when you insert, you will have x1. You will have the operators x1 power n, x2 power n, xn power n, and you have lambda 1 power n, lambda something like this. Then you can club you can take, using this constant, you can write this something minus the corresponding lambdas power here. And then using triangle inequality, it is enough to prove each term by term goes to 0. So term by term, if you want to prove that, that is, so I do it for, I tell you for two variable, and I mean two variable, and then erase it. Okay. If we have something like this, x power n, y power m. Okay, some x power n, y power m, lambda 1 power, say x1 power m, x2 power m, suppose lambda 1 power n, lambda 2 power m. Okay, this is what you want to think about. Now you can write this as x1 power n, x2 power m minus lambda 1 power n, x2 power m plus lambda 1 power n, x2 power m minus lambda 1 power n, lambda 2 power n. Now you can take this. Now use triangle inequality. You can take this and you can write it as x1 power n, lambda 1 power n. And then something x2 power n, you can take it outside. And that's a finite thing, which is, I mean, there is, which is just the m and n, all these things are fixed. So you will get another constant that will go out. And then you have x1 power n minus lambda 1 power n, which you can write it as x1 minus lambda 1 into some like this, some n variable, no? N sum. You can write it, no? A power n minus b power n equal to a minus b into a power n minus 1. You can write it like this. Okay? You will write it. And that will be, if you club it all these things together, then you will get some finite constant. Okay? Then you will get a minus b, and you know that it is a minus b times that goes to 0. All other things you can take out of the norm, and you can show that this goes to 0. I'm sure it's easy. It is just a bit messy. I think you can do it. I don't want to give it as an assignment. I assume you do it. But you better do it, because if I ask this question in the exam, then you have to write the solution. Okay. So this is an exercise. Okay. So we know, so we have proved that this implies whatever we have proved, this implies what? This implies the left hand side. P of sigma x1 to xn is contained in sigma of P of x1 to xn. Okay, we have proved this way. Is this clear?
Yes.
Okay. If you do this exercise, that will be clear. Okay. Now to prove this direction, which is actually the other direction. Now to prove sigma of P of x1 up to xn is contained in P of sigma of x1 up to xn. Now we want to prove the other direction. Okay. How do you do it? We take a lambda one second. I just forgot the argument. So we have the earlier thing, so that's correct. What do we do is the following. We just join this x1 up to xn with the, so, okay. So we need to do the following. Oh, I forgot to say that this P of x1 up to xn is normal. That is clear, no? You have x1 up to xn. You are taking the complex polynomial and inserting this x1 up to xn, which is a polynomial and x1 up to xn. Okay. And if you take the star, that will just, the constants will become a bar. And since this x1 up to xn commute with each other and they are self-adjoint, and it is just the p bar of x1 up to xn. Okay. And then if you, everything commutes with each other. I mean, if you take scalar times, it is clear that it's normal. Okay. So p is normal, p polynomial times this x1 up to xn is normal, is clear. Okay, just check it. So this is exercise. Okay. I mean, normal means something commutes with its star. If you take p of x1 up to xn, if you want to take its star, it is just the taking the bar and the coefficients of the polynomial. because they are all self-adjoint, they are all commuting. It will just remain as the polynomial will remain as it is. So it is just p bar, and the p and p of x1 up to xn, p bar of x1 up to they are commute because all these things are commuting. Okay, so it's normal. Okay. Now, if you have any polynomial p, okay. Now, first the claim is the following. First notice or claim. If you remember, we proved the following long back. So, note to recall. If lambda is in sigma of some x is self-adjoint. Okay. No, it's x is normal. Sorry. So I will use t. X may be confusing because I'm using it for self-adjoint. T is normal. And lambda equal to alpha plus I beta. Okay. And t equal to x plus iy, where x and y are self-adjoint. Okay. Then alpha is in sigma of x. For normal operators, alpha is in sigma of x and beta is in sigma of y. We proved this. In particular, if you take, and there exists, not just that, there exists joint approximate eigenvector for x and y. That is, there exists joint xn such that alpha x minus alpha xn, both y minus beta xn, these both goes to 0. Okay. We proved it when we discussed, before we started doing all this spectral theorem and the functional calculus, before that in the preliminary we proved this. Okay. This is very easy, direct. Okay. The proof is direct. So because of that, if we want, so what do we want to prove? We want to prove the sigma of this is contained in this. Okay. So if you have any lambda in sigma of that will be sigma of p of something. So that p of that x1 up to xn can be written as p of, the polynomial p can be written as some q plus ir, where q and r are real polynomials. Okay. Then this p of x1 up to xn equal to q of x1 up to xn plus I times r of x1 up to xn. Notice that since this q and r are real polynomials, these are all self-adjoint operators. R of x1 up to are self-adjoint operators. So p of x1 up to xn is this decomposition of p of x1 up to xn as self-adjoint. This plus this. So if lambda is in the spectrum of this, if lambda is in the spectrum of p of x1 up to xn, and lambda equal to alpha plus I beta, okay, then this alpha is in the spectrum of q of x1 up to xn, and beta is in the spectrum of r of x1 up to xn. Okay, and then the approximate eigenvalue, whatever that is satisfied, jointly satisfied also. So we want to prove that the sigma of p of x1 up to xn is contained in something. Okay, polynomial of something, and that p is q plus ir. So this will also split into q of that set plus I of r of that set. Okay, that is how it is split. And we know, so we will be able, so if we, and this will also become sigma of some q of something plus I times sigma of q of something. So it is enough to prove that this, I want to say that they are enough to prove this statement for real polynomials. So because of all these things, if we just go through, because of all these things, enough to prove, without loss of generality, we can assume P is real. Okay. Because of all these things. We want to prove this is, oh, I erased it. We want to prove that this is contained here. And real part of this is contained in real part of this, imaginary part of this contained in imaginary part of this, that is enough to prove. But then that corresponds to the P, the return as, I mean, you get some imaginary part here. I mean, all the other things are real. I mean, the sigma of x1 up to xn is a real subset of real Rn. But then if you take polynomial, that can become complex. Okay. Similarly, sigma of a normal operator is contained in complex numbers, which has real part and something. So the real, so I mean, that complex part of P of that comes from the complex polynomial. But if you split that polynomial as a real part and imaginary part, the corresponding thing will also, here also it will split as real and imaginary part. It's enough to show that the real part is contained in the real part, imaginary part is contained in the imaginary part. So it is enough actually to prove that for the case when P is real. So that's what all I'm saying. Okay. It's enough to prove that we can assume that P is real. So when P is real, then the polynomial of x1 up to xn is self-adjoint. Okay? That is, P of x1 up to xn is self-adjoint. Okay? And you call that as xn plus 1. Okay? Then we consider this sigma n plus 1. So now by earlier proposition, previous proposition, if lambda is in sigma of n plus 1, then there exists lambda 1 up to lambda n in sigma of x1 up to xn, such that lambda 1 up to lambda n and lambda, this is in sigma of, we proved it just sometime back, xn plus 1, right? That's what we proved. That is, there exists xn. This is what we proved, no? The last proposition. To prove the last proposition, we had a claim, and that is what this claim is, right?
Yes, sir.
Okay. So this means there exists xn with norm xn equal to 1, such that lambda xi minus, this is lambda. Okay. Xi lambda, you call it as lambda n plus 1 also. Okay. Xi minus lambda I of this xn. Oh, this should be xk. Sorry. Norm of this goes to 0 as k goes to infinity. Okay. Okay. In particular, this is for all I. This is for all I in n plus 1 and greater than 1. So now it is true for 1 up to I, 1 up to n. But we have just proved that if something is a giant, I mean the first part, we proved that, see here we proved that if xi minus lambda I xk goes to 0 for all I between 1 to n, then any polynomial of x1 up to xn to polynomial in xn, that also goes to 0. We just proved it. So because of that, this implies polynomial of x1 up to xn minus, I mean that was an exercise which I gave the argument orally. You have to do some manipulation of lambda n. This x k goes to 0. Okay. But then by our assumption, this p of x1 up to xn, this is what we called it as xn plus 1, right? That's what we assume, call it as xn. So minus p of this lambda 1 up to lambda n xk goes to 0. But we also have norm of xn plus 1 minus this lambda n plus 1, we call it as lambda, okay? Lambda of this xk. This also goes to 0 as k goes to infinity. Okay? This will imply lambda should be equal to that. If you want, we can write it as this lambda minus p lambda 1. I mean, this is if you have any lambda and mu satisfied this, lambda has to be equal to mu. So lambda 1 up to lambda n. These are numbers. Okay, I'm just putting modulus. This modulus is equal to modulus of lambda minus because that you can insert xk, because norm xk is 1. You can insert xk, okay, and this is less than or equal to p of that, sorry, xn plus 1. Xn plus 1 minus lambda times this xk plus xn plus 1. I'm just adding and subtracting that, minus p of lambda 1 lambda n xk, and both these goes to 0. So this implies lambda has to be equal to p of lambda 1 up to lambda n. That's what we want to prove. That means lambda is in p of sigma of, I mean, we know that this lambda 1 up to lambda n is in the sigma of this. That's what our claim is. Okay? Sigma of p of x1 up to xn is contained in p of sigma. Okay, so we proved the proposition. Any problem with the proposition? Anyway, it's all in the book. I have just restated all the argument, maybe with slight changes, whatever came to my mind now. Okay? It's the same argument, possibly with more details. I just give. Okay? Okay, the corollary. What is the corollary? So if we have a p is a polynomial, p is I mean, this is polynomial, C polynomial of sigma of x1 up to xn. Okay? Right? Then norm of p in this sigma of x1 up to xn equal to norm of this p of x1 up to xn. Right? Is this true? Norm of p x1 up to xn. This is just a normal operator. So this is equal to the spectral radius of sigma of p of x1 up to xn. Right? But then spectral radius is just the supremum of lambda in sigma of p of x1 up to xn. Right? But then this is equal to supremum of p of this is just supremum of p of lambda 1 up to lambda n, where p of lambda 1 up to lambda n, where lambda 1 up to lambda n is by the spectral mapping theory, because that is equal to p of that. I mean, supremum of lambda in here, if you want, you can write it supremum of lambda in p of sigma of x1, which is equal to p of lambda 1 up to lambda 1 up to lambda n is in sigma. So, which is just basically equal to norm p. Sigma, sorry, x1 up to xn. Okay. Just direct verification.
Like there should be modulus everywhere, right? Supremum of modulus of lambda.
Yes, you are right. Modulus, everywhere modulus. Yeah, everywhere modulus. Okay. Okay.
And it should be R of P of x1 all the up to xn. There should
R
not
of?
be like you wrote R of sigma of P of.
Sure. Right? Fine. Yeah. Okay. Good. Thanks. But that's what I meant. Okay. So now we prove what is called the functional calculus. So now the corollary is the following. What does this mean? This polynomial functional calculus preserves the norm. So by Stone-Weierstrass theorem, polynomials are dense in the corresponding continuous functions. So we can extend it to the corresponding continuous functional calculus. Okay. So maybe I will. So it's 6:30. I'll stop and I mean it's just a restatement of what we approved. But anyway, since I'm going to recall next time, I will state it in the next class. Okay. So if you have any doubt, you ask me. Otherwise, I will end this session. Okay. So no question. You can ask me next class. Goodbye.
Thank you.
Okay. Thank you.